So we put a little bracket. So we find the antiderivative, and then we put a bracket. And then here's our next step. We're going to take this upper limit, whatever it is, and we're going to plug it in for all the x's, for x. So basically, we're figuring out what the antiderivative is at b, at the upper limit. Like we get a number. And then subtract whatever we get when we plug in the lower limit. This right here is the fundamental theorem of calculus. So we find the integral, we plug in the upper limit, we plug in the lower limit, and then we subtract the two values. In the end, you're going to get a number answer like 6 or 10 or whatever. You're going to get a number out in the end. And that is what the area under the curve will be. Okay, that's our process. So example 1 says evaluate the definite integral of x squared plus 3 from -1 to 2. A refresher of what this is asking, in case you didn't watch the video, or in case you did and just didn't understand, this is saying if you had the function x squared plus 3, so imagine that parabola, the normal parabola shifted up 3 units, okay? So this parabola right here, that's the function. And then we want to find the area from x being -1 to +2. So basically, this definite integral is wanting to find this area right here. And we have no way with geometry, we have no way to find that actual area. We have that curved surface in there. We don't know how to do this. But this is what a definite integral does. This is going to find that exact area for us. So here's how it works. The first thing we need to do is integrate x squared plus 3. We have to do our power rule. So we bump it up to x cubed and then divide by 3. So I'm going to write that as 1/3 x cubed. And then plus 3x. So that's the antiderivative. That's the integral. Then we're going to put a square bracket, and we're going to put -1 to 2 right here. Now what I'm going to do is take that upper limit and plug it in for all the x's here. This is like capital F. This whole expression is like capital F of x. Now I want to take that upper limit and plug it in to these x's here. So I'm going to plug 2 in for both these x's. So it's going to be 1/3 2 cubed plus 3 times 2. So all I've done is plug in the upper limit. And then I find a lot of students tend to make mistakes with the subtraction part because now we need to subtract. So here's my advice. Right when you plug in or finish plugging in the upper limit, then put minus parentheses because you're going to be subtracting whatever you get when you plug in that lower limit, the entire quantity of it. So as soon as you finish plugging in the upper limit for the x's, put minus parentheses and now plug in -1 for both these x's. Now you're putting -1 in for both x's. So it'd be 1/3 and then -1 cubed plus 3 times -1. This is it. It's all numeric at this point. This is the area under the curve. Now, I want to point out, and because we haven't talked about this in quite a while, but remember, if you're doing a free response question, it doesn't matter how nasty your answer looks. If it's all numeric, leave that answer. Like if this was a free response question that I had to do, I'd be like, all right, good luck, grader. I'm not joking. I would leave that and they give you 100% credit. I know it looks gross, but I would 100% leave that. And I encourage you guys, when you do your tests in here, leave those answers for me to grade. Practice that. There's nothing worse. I get so sad when students do this. They'll get here, it's all right, and then they'll do something stupid and say 2 cubed is 6. And then everything's wrong. Like you lost all your credit. So if you don't have to simplify all that, please don't. All right. The answer to this is 12. If that makes you like uncomfortable, the answer is 12. But you are allowed to leave your numeric answers like that. So that is the fundamental theorem of calculus. You integrate, you plug in the upper number, you plug in the lower number. Baba, you got a question?
Yeah.
What's up?
Why don't we put plus C when we integrate?
Look at the next line. It's like we planned this, man. So the very next line says, why don't we need to put plus C? Like, why didn't I put plus C when I integrated when every other time we've had to put plus C, right? So very good question. Here's the reason why. You technically are on these putting plus C, but I want you to look at why we don't have to. So imagine that when I integrated, I did put plus C, okay? Imagine I did. So right here on the end, I put plus C, just like all the other problems we did, okay? Then I would plug in 2 for the x here and the x here, and then I would have plus C. And then I would put minus parentheses, and then I would plug -1 in for the x here and x here, and I would have plus C on the end here. And then what will happen every single time, you'll have plus C here, and then you'll have minus, and this minus sign is going to everything inside the parentheses. So it'd be like positive C and then minus this C here. And it's the same C value. So it's going away every single time. So you could put it, but it's just not necessary because through the math, it's always going to cancel out. So with definite integrals, you don't have to put plus C. It's not wrong to, you just don't have to. That answer your question?
Yeah.
Word. All right. So last semester, I made a comment. When you guys have your calculator at your disposal on free response questions, there's a lot of things you guys are allowed to do without showing any work whatsoever. The big one we did last semester was Math 8. You guys were allowed to find derivatives at locations with your calculator without showing any work whatsoever. You push Math 8, you get your answer, right? Another thing you're allowed to do without showing any work, I'm going to show you guys this in the calculator. You guys are allowed to do definite integrals in your calculator without showing any work whatsoever. Like if you have a calculator, if it's question 1 or 2 on an FRQ, and you have to do a definite integral, you will never find the actual antiderivative and plug this stuff in. You won't. In fact, the problems they'll give you, you probably won't even be able to if you have a calculator. Like you'll have to use the calculator. So I want to show you guys how to enter this in the calculator because it's one of the things that, number 1, they let you do for free with no work. And number 2, you probably have to. All right. So when we do derivatives, we do Math 8. I push Math, and I scroll down to option 8, and it says NDeriv. And that's where you type in your derivative, and then your function, and then you put in the number. With integrals, if you're doing a definite integral, it's the next one. It's Math 9. Finins. So if I push Math 9, now it just pops up. If you have an 84 plus, the notation is awesome. Now I could just put in my -1 for my lower limit, 2 for my upper limit, put in your function. Oh, shoot. I was in, we were doing parametric functions in BC, so I was in parametric mode. You guys remember parametric functions from pre-cal? No? Do you remember hearing them? Oh, they remember taking a test on it in honors pre-cal. Right when we went on quarantine, they said you guys had a big test. I don't know if you did it. Maybe. You what?
Was it at home or?
Probably. It's parametrics. I don't know if this will. So I got 12. I got the same answer. Parametrics are ones where they have like they define it in terms of t. So like you have 2 functions. You guys remember doing those? You do? You don't? Maybe you just tuned out at the end. All right. You don't have to worry about it. So we don't get into it in here. What's that? Huh?
Cheney remembers, I'm sure.
Cheney, do you remember doing those?
Yeah. Yeah, I do.
All right. Okay. Next one. Evaluate the definite integral from 0 to 2 of 2 minus t times the square root of t dt. So yeah, we could just push math 9 in our calculator. We're not going to do that though. We are going to do this by hand. So Alyssa asked a question on the homework with the product. And I said there is no product rule for integration. Like at this point in time, I can't integrate this as I see it. But what I can do, which we've done a little bit of, I can take this square root of t, or t to the 1/2, and distribute it inside the parentheses here. And then I can just do my power rule. So there are, before you just integrate right away, sometimes you do have to kind of manipulate a little bit. In fact, there was one on the quiz. I don't know if you guys remember or not. I don't have it. You had to integrate a fraction on the quiz. You had to integrate, it was like x cubed plus x over x or something like that. I don't remember exactly what it was. But when you're integrating fractions, the first thing you have to do is divide both of these by the denominator and make this be x squared plus 1 instead. My point is sometimes you have to manipulate before you just jump into the power rule. That's my point. So for this one, we're going to take, this is t to the 1/2 right here. So we're going to take t to the 1/2 and distribute it into the parentheses. So we would have the integral from 0 to 2 of 2t to the 1/2. And then t times t to the 1/2. To combine those, we have to add the exponents. So that would be t to the 3/2. Keep in mind, I haven't integrated anything yet. I've just gotten to a point where now I can integrate. So now I'm going to do the power rule. I'm going to integrate this. What I find, like this is not extremely complicated procedure. You integrate, and then you plug in the top number and bottom number. What happens as the semester goes on, students will forget to integrate. They'll forget that part. They'll come into this problem and plug 2 in for these t's and plug 0 in and just subtract them and never integrate. Make sure you integrate first. So I bump this up to 3/2 and then divide by 3/2, which is like multiplying by 2/3. 2 times 2/3 is 4/3. That's a lot of mental math. But basically, I bumped the 1/2 up to 3/2, divided by 3/2. So I multiplied by 2/3 instead, got 4/3. Same here, bump that up to 5/2. Divide by 5/2, you'd have 2/5 in front. Put my brackets. So I'm doing that from 0 to 2. And then I'm going to plug 2 in for the t's and 0 in for the t's. So I plug in the upper limit. I plug in 2 for both t values. And then as soon as I finish the second one, I would put minus parentheses. Always. That way you don't have to mess with that negative. It doesn't cause much confusion. The nice thing on this one, when one of your limits is 0, if I plug 0 in for these t's, they just go away. So I don't even have to worry about the second part. And I am not going to mess with this one. This is my answer. I'm not dealing with that stuff. And I say, good luck, grader. They won't be mad at you. I promise. All right, next one, a little triggy. Get triggy with it. So I think on the notes, I have it from 0 to pi. I want you guys to change it from 0 to pi over 4. I want you to change the upper limit on the notes to pi over 4 instead. All right. So first thing we have to do is integrate cosine. What's the integral of cosine? Negative sign. What do you say? What do you say? It's just positive sign. And it's easy to mix the signs up. I get that completely because last semester, every single time we would differentiate cosine to get negative sign. So it's easy to make that mistake. So just in your mind, like when you're integrating, just know the derivative of sine is cosine. Like if you have that, then you'll be in good shape. So integrate cosine, we get sine. And then we plug in pi over 4 and plug in 0. So just like, and we're going to evaluate this, but I've mentioned this, but again, I know a lot of things, it's hard to remember a lot of things. So just like I said, if it's all numeric, you guys can leave that. The same goes with trig functions. If it's a free response question, you guys don't have to evaluate or analyze any trig functions ever. Like if you just left this answer, let's say you're sitting taking your test and you're like, ah, crap, I don't remember the sign of pi over 4. Just leave this answer. You get full credit. Now, you do have to know the unit circle. If it's multiple choice, you have to know that this is square root of 2 over 2. And sine of 0 is 0. Like we have to know those things. But if it's free response, you don't have to at all. So I don't know when I usually bring this up, but I'm just going to bring it up now because I'm not sure. What we are doing, yeah, we're finding the area under a curve. But who really cares? How many of you guys are so excited now to be able to find the area of that little shape right there? Like you were just dying to know. No one cares? How dare you? What definite integral really is, when you're doing a definite integration, it's actually finding how much the original function changed from one time to the next. That's what this actually is. And when you guys get into some questions, like you guys are going to have to integrate velocity a lot. Let me say that again. You're going to have to integrate velocity a lot. And I want to explain why. Okay. What it finds. You guys remember last semester when we would find the slope of a tangent line? And then we found another slope of a tangent line. It was like, who cares? Well, what slope of a tangent line is, it's finding the instantaneous velocity at a moment in time, like how fast something is moving at one instant moment in time. That's a little cooler. I don't know if you guys care about that at all, but to me, that's a little more interesting than just slope. And that's the same with definite integration. Yeah, it finds area, okay. But what it's finding is from one time to the next, how much did the position change? You don't need to write this, but I want you to see what will happen. A lot of times, you're going to have to integrate velocity, okay? I'll show you what happens. So if you integrate velocity, what do you get back to? You get back to position, right? So if I do this definite integration, and I'm not thinking about it in terms of area, okay? If I integrate velocity, I get back to position from 0 to 4. And then I plug in 4, take away position at 0. So what this is actually finding is how much the position changed. Like x of 4 is where you are at the end. Like you're moving all over from 0 seconds to 4 seconds. Watch me walk from 0 seconds to 4 seconds. 1, 2, 3, 4. I stop here, okay? X of 4 is where I am now. X of 0 is where I was to start. If I subtract those two things, it tells me how far I went. That's what we get into here. Definite integrals, yes, it finds area, but more importantly, conceptually, it finds how much the original function changed, okay? And I stress this because the FRQs you guys are going to get, they are crazy messy and involved. But pretty much, they're always going to give you a function as a rate of something. Like a couple years ago, they gave the rate at which a stock boy was stocking bananas on a shelf. One year, they gave the rate at which snow was falling. One year, they gave the rate at which fish were being stocked into a pond. And if you integrate those rates, you get back to how many like things actually went into the stuff over time, like how much snow fell, how many fish were put into the pond, how many bananas were put on the shelf. So if you integrate the rate of something, you get back to how much the original thing changed over time. That's when I think it gets kind of cool. So anyway, I'm excited. All right, next one. So I want to evaluate the integral of the absolute value of x minus 2 from 0 to 3. Okay. So I made a comment last semester when we were doing derivatives with absolute value. I pretty much said anytime you have absolute value show up, sketch a graph. Because there is no integral rule for the absolute value of x minus 2. I don't know what the integral of absolute value of x minus 2 is. I can't integrate this by hand. But if I sketch a graph of the absolute value of x minus 2, I want you guys to see what happens, okay? So let's say I want to graph the absolute value of x minus 2. So I draw a little coordinate plane. And I don't know how much you guys remember from Algebra 2 and Pre-Cal, but the absolute value graph is the V shape, right? And if it's the absolute value of x minus 2, that's an inside change. So it's shifted to the right 2 units. You guys remember, you did a lot of that in Pre-Cal, right? A lot of shifting, manipulating. So the absolute value of x is this V shape here. And then we're shifting it to the right 2 units. So it looks something like this. You're going from 0 to 3. If you're someone who you're like, I would not remember that shifting whatsoever, then make a little table of values to draw a rough sketch. Like if I plug 0 in for x, I get positive 2. So I put my first point at 0, 2. If I plug 3 in for x, I get 1. So plot another point at 0, 1. And if you would plug 2 in for x, you get 0. 2 is where the turning is. But there's the graph. All this question is saying, this is saying find the area under this graph and above the x-axis. It's basically saying find the area of those 2 triangles and add them together. So again, my advice, if you guys come across absolute value, if anything in this class, sketch a graph. Absolute value is too hard to work with algebra. So I just got to find the area of each little triangle. So this is, let's see, 1/2 times 2 times 2. So 2. And then 1/2 times 1 times 1. So 1/2. So 2.5. You may, on the AP test, have to do something like this, and it's pretty messy, but they'll give you a calculator if they do. So I want to show you guys how to integrate with absolute value. I just want to refresh your memories on where the absolute value button is. So if I wanted to do this in the calculator, well, I would push math 9. I would go from 0 to 3. And now I got to put in the absolute value of x minus 2. So the absolute value symbol is under the math menu. So on the left column, if you push math, and then you arrow to the right one to number, that option there says ABS for absolute value. So you can enter the integral of the absolute value of x minus 2 with respect to x. Now your calculator, when it's doing a definite integral, it's actually doing a Riemann sum. Your calculator doesn't know what these answers are, but it's putting in a ton of rectangles and very quickly computing the area of all those rectangles and adding them up. And that's why sometimes when you do one, you might get an answer that is a little bit off. But if ever you get like 0.00000, you can knock that stuff off. Calculators are so smart. What do you guys think so far? Is your little brain okay? For now. That's what I'm saying. Okay. Okay. Just want to make sure we're all good. So we got 2 more big ideas to talk about. That was one. Kind of two. Like doing the fundamental theorem of calculus, the process is big idea one. Big idea two is understanding that you're finding change in the original function. Just kind of having that on your mind. I don't think I've brought that up on these notes before, but I think it comes up in the homework tonight and questions come up. So that's why I wanted to address it kind of now. Okay. The next thing is big idea, I don't know, 1.5, 2.5, 2, 3, I don't know. What does it matter? Okay, so first semester, we learned a mean value theorem. We learned a few theorems. The two biggest theorems from first semester you'll have to know is mean value theorem, it's probably the biggest, and then the intermediate value theorem. And those will come back as we start reviewing for the AP test, so don't worry at this point in time if you don't remember those. But the mean value theorem from semester one said this. If you had a continuous and differentiable function and you found the average rate of change over the interval, the slope from, that's the worst line I've ever drawn. If you find the slope from one endpoint to the other, there's some point in the interval, there's somewhere in here whose instantaneous rate of change would be the same as the average rate of change. That was the mean value theorem from first semester. Notationally, it said there's some point where the derivative equals the average rate of change. And then in the problems, you had to find it, yada, yada. That was the mean value theorem from semester one. There is a mean value theorem for integrals. Here's what it says. For this, and you don't need to know this by name, so don't worry about knowing this theorem by name or anything. It says if you have a continuous function, then there exists a c value in the interval such that, now I'm going to write this, and you're going to look at it and be like, okay, that doesn't make any sense. And then I'll make it make sense. But there's some c value such that the integral from a to b, so this is the area under the curve. Like this is the exact area under the function. There's some c value where this is true. There's some c value where if I plug it into the function and I multiply by the width of the interval, I get the exact area under the curve. To make that kind of make sense, so we've done Riemann sums where we've put in several rectangles and added them up. Imagine I just drew one rectangle, right? In the lesson video with Riemann, I don't know if I did in lesson or in here, I forget, but when we put in like 3 rectangles, it was a terrible approximation. Imagine I put in one rectangle. It's gonna be booty, it's gonna be brutal. Like imagine I start at the left endpoint and I go up and I go all the way over. Is the area of that rectangle the same as all the area under the curve? You're so smart, Brooke. Brooke said no. No, it's not at all. Imagine I take that rectangle and let's say I started at the right side instead. So I start at B and I go up and I go all the way over to A and then I go down. Brooke, is the area of that rectangle the exact same as how much area under that curve? No, you're good. What this theorem is saying is there has to be some point in the interval, some place where if I draw one rectangle up to that height, the area of that rectangle will equal the exact area under the curve. I'll kind of eyeball it here. Here maybe. So if I draw one rectangle that spans A to B, I'm going to kill this pencil. Up to that height. Brooke, if I find the area of this rectangle, is that the same? Does it look to be about the same as the area under the curve? Yeah, because I have not enough here. I have too much here. I probably could have went over to the right a little bit. But you get the gist. There's some c value in the interval that the rectangle's area is going to equal the area under the curve. Now that's not really a big deal so much as what it leads to. Like this right here is not a formula you guys are going to have to know. What I'm about to show you is a formula that you guys are going to kind of have to have memorized. Okay. So the average value of, bless you, the average value of a function, f of c, this height right here, whatever this height is that makes that rectangle happen, is known as the average value of that function. Right? This function has a whole bunch of y values. I'm going to put a number here. Let's say that number is 4. I'm just completely making this up. And let's say that number is 6. So right here, this function has a height of 4. Here it's like 4.1, maybe 4.4, maybe 5, 5.8, 5.9, 6. Has a whole bunch of y values. But if I wanted to know what's the average value of that function, the average y value over that interval, that's what f of c is. So this becomes super important, being able to find the f of c value. So if I take this equation and I want to get f of c by itself, I'm going to take both sides and divide by b minus a. I'm going to divide both sides by b minus a. So the average value of a function, which is f of c, is equal to 1 over b minus a. That's me dividing both sides by b minus a. Instead of putting b minus a under the integral, which looks kind of messy, we just put 1 over b minus a out in front, times the integral from a to b of f of x. This is a super important formula. You're guaranteed to see an average value question pop up probably at least twice on the AP test, for sure once. Like there's some things I've taught you guys that I can't guarantee will show up on your exam. They might not. This is something that will show up 100% at least once, and usually this shows up at least twice, finding the average value of a function. One thing I want you to notice is, and I'll try to make this make more sense, probably next class when we go over the homework and stuff, but I want you to notice that if you're finding the average value of f, you integrate f. Whatever you're finding the average value of, that's the function that goes inside the integral. That becomes really important. And I'll get a lot of students that once you do some more problems, students will say, what's the, how do you know when to do the slope formula? And so I pulled out a couple FRQs to kind of show you, because the questions are not always just going to say, hey, find the average value of f of x. They're going to say, find the average temperature. They're going to say, find the average number of fish in the lake. Find the average number of bananas on the shelf from time 0 to time 5. Like they're going to use the word average, but in context. And so I pulled one out. I was going through my stack over here. And I want you guys to look. You don't have to read the question. Please don't, because I don't want your head spinning more than it is. But I want to hone in on a couple phrases. In part A, it says, find the average rate of change of A of t. When you guys see the phrase average rate of change, that is slope formula. That has nothing to do with integration. That has everything to do with what we learned first semester, where you do f of b minus f of a over b minus a. So average rate of change is slope. That doesn't change. But I want you to look at part C. Part C, it mentions the average amount of grass clippings in the bin. This is a tip off to me. That's an average value question. It says the average amount of grass clippings in the bin. So when you see the word average, if it says average rate of change, that's slope. And if it says average amount of something, that's this formula that I just taught you guys right here. Okay. We're going to do a practice problem with that. So 5 says find the average value of f of x is 3x squared minus 2x on 1 to 4. Then find the c value where the average value occurs. Okay, so as soon as I see average value or average temperature or average whatever, that tells me I'm doing 1 over b minus a times the integral from a to b of that function. I think it's a good habit once you learn like a formula, just write it several times. If I'm finding the average value of f of x, I'm going to integrate f of x. So it's from 1 to 4. So I would do 1 over 4 minus 1, so 3. And then integrate from 1 to 4. 3x squared minus 2x. That's the new stuff. Now I just do what we did at the beginning of the lesson, the fundamental theorem of calculus. I need to actually figure out what this integral equals and multiply it by a third or divide it by 3 or whatever. So I got to figure out what that integral equals. So step 1, I'm going to integrate 3x squared minus 2x. So that would be x cubed divided by 3. So just x cubed. And then minus, let's see, x squared divided by 2. So x squared. And I'm just keeping that 1/3 out in front. Now I'm going to plug 4 in for both x's. So I plug in the upper limit now. So 4 cubed is 64 minus 16. And then as soon as I finish the last one, I do minus parentheses. And then I plug in the lower limit. So I'm going to plug 1 in. So 1 minus 1. So 0. That's 48 times a third. So 16. So that's the average value of f over the interval from 1 to 4. Then it says, then find the c value where this average value occurs. So when it says find the c value, now I want to know, okay, if the function equals 16, what x value makes that happen? So I set my function equal to 16. And then I have to solve this. So I'm going to set it equal to 0. Any quadratic ever, set it equal to 0. And at this point in time, you would just have to factor it or quadratic formula, whatever, however you want to handle this. I'm just going to give you the answers. So if you did the quadratic formula or you factored it or whatever, you would get x equals 8/3 and -2. But thinking back to first semester, when we're dealt with intervals, we always have to make sure that our answers are within the intervals, right? You do all this work and then you get answers. And so it's such a nice feeling. You get answers and then you move on. Always make sure you check. -2 is not in the interval from 1 to 4. So 8/3. So that's the average value formula. Comes up a lot. Here's one. We're going to do a lot of FRQs here starting in about a week or two, like a ton of practice of these. Like most days we're going to start and you guys are going to work these out. So I put these up not for you guys to know how to do them at this point. We'll practice them. But for this one, I'm putting up just to show you again, right here in part B. So they give all this context talking about temperature of some metal wire. Yeah, that's irrelevant. But the question says, write an integral expression in terms of T of X for the average temperature of the wire. As soon as I see like average temperature in my brain, that's a tip off. That's an average value problem. I'm using the average value formula. And if you can just key in on little phrases like that, it makes the problem so much more manageable. You can kind of take all the context out of it and just know, oh, I know the average value formula, and then apply it. That's how I go into these FRQs. They get scary. Even for me, I read them and it's like, Jesus, what do they want me to do now? But if I hone in on stuff like that, it just makes the problem so much more manageable. All right, last big idea, and probably the easiest. Hopefully that'll make you feel better. The last thing we're gonna talk about is probably the easiest thing of the day, okay? So we did the fundamental theorem of calculus. That's what we've done so far. There is a second fundamental theorem of calculus. It's even easier than the first, okay? If you have some continuous function, ignore all that. Here's what's true. If you take the derivative of some integral I'll wait for you to write this. Here's kind of the setup. You're taking the derivative of an integral. That's kind of what's happening. Taking the derivative of an integral. And the lower limit can be any number in the world. They just put a here. A could be any number in the world. In this problem, they had it be a 3 in example 6. In example 7, they have it be a 2. It doesn't matter. The number does not matter. It could be a billion. It's irrelevant. The point of the second fundamental theorem of calculus is basically, you know how if you add 5 and subtract 5, they undo each other? And when you multiply by 5 and divide by 5, they undo each other? Well, a derivative and an integral undo each other. They cancel each other out. So they're inverse operations. If you're taking the derivative of an integral, the derivative and the integral cancel, and all you're left with is the function that was inside the integral to begin with. What happens is this upper limit, that's an x, becomes our new independent variable. So if you take the derivative of an integral, all you're left with is the function that was inside the integral to begin with, because derivatives and integrals cancel each other out. So if I look at example 6, and it looks crazy messy at first, right? You got derivatives, you got integrals, one of the limits is x, you got radicals. But all they're wanting you to do, if you differentiate an integral, all that happens in this problem, this x, this upper limit, just pops right in place of the t, and everything else inside the integral stays the same. Like this function is all we're left with. It'd be the square root of x squared plus 1. No work to do. And then the last thing, if your upper limit is something other than just x. So normally when you guys do problems on the AP test or on problems in here, almost always the upper limit is going to be x. Almost always. But if the upper limit is something other than x, like x squared or 2x plus 1 or whatever, some function of x, we treat it very similarly. So this says find f prime. What that means is I want to differentiate both sides. If I want to find f prime, I want to find the derivative of both sides of this equation. Okay, so I'm going to say f prime of x equals, and then I'm going to differentiate the right side. Here's what the notation looks like. You would not need to write this line, but I just want you to see good notation. So f prime of x is whatever I get on the right side. Well, we just said a derivative and an integral cancel each other out. So what's going to happen, this upper limit, whatever it is, goes in place of your t. So it's going to be 1 over, and instead of it being x cubed, it's going to be x squared cubed. So whatever the upper limit is, pop that in for the t, for the variable, whatever's in there. The only other thing you have to remember is it's kind of like chain rule, how then you have to multiply by the derivative. Well, if the top limit is something other than x, we then have to multiply by the derivative of the upper limit. So we put the upper limit in, and then we multiply by the derivative of the upper limit, which would be 2x. Like I said, it's typically just an x up there. I've seen an occasional problem where it's not. Using some exponent rules. Got through this lesson a lot quicker than I was anticipating. Like 23 minutes. Yeah, the lesson's over. But I want to show you guys kind of where, because a lot of students will look at that and be like, that's stupid. This thing, just the x popping in. But I want to show you guys the problems that they're going to ask. This is one of the most common questions that they ask on free response questions. They give a graph. You don't have to write this. This is from 2016. They give a graph. And what happens is this. I want you guys to look at this because this will become really important and we'll practice them. They give a graph of f. So look at this. They give the graph of f. But then look at all the questions in the problem. All the questions revolve around g. Does the graph of g, absolute maximum value of g, all about g. And so look right here, they define g as the integral of f from 2 to x. So when they define a function as an integral, here's what's kind of neat and nice. If I differentiate both sides, just like we did on the last example, if I differentiate both sides, I would get g prime of x equals, and what would I get on the right side if I differentiate this? What would this become? Just f of x. Yeah, the integral will go away. So what this means is, yeah, they give you the graph of f, which is cool and all, but really they're giving you the graph of g prime. So if you're given the graph of g prime, now I can answer all these questions about g. So they'll define a function in terms of an integral. We'll just differentiate both sides and then not worry about f. That happens a lot. This was the most recent FRQ. They did the same thing. They give the graph of f. This one's a little bit different, but anyway. All right.
Mr. G,
Yeah.
do we have to worry about the lower bound when we do that?
No, not for right now. That lower bound will have a meaning. I don't want to get into that today. That might come up in a class or two. But no, for instance, on this example that I just put up, if that lower bound was 2000, then this would still be true right here.
Okay.
Unless you guys are curious why it doesn't matter. Are you? You don't have to write it, but the reason it doesn't matter, I'll show you. I already did it, so instead of me doing it again. So imagine that I had this problem here, okay? That I say, hey guys, find the derivative of the integral from 2 to x of t squared plus 2. And I actually wanted you to go through and do, let's pretend we didn't know this little shortcut. And you had to go through and do the math, right? So if I was going to do the integral here, well, I would integrate t squared plus 2. That's this, from 2 to x. Then I would plug x in for t here and t here. So that's what this is, just x cubed plus over 3 plus 2x. Then take away whatever I get when I plug 2 in for the t's. That's what this is. Then the last step is take the derivative of all this stuff. Differentiate it. Well, when I differentiate all this stuff over here, I'm always going to get 0. Like no matter what that bottom number was, even if it was 2000 and I plugged 2000 in for these letters, this would just be a bigger number. But when I differentiate it, it goes away. So it doesn't matter what that bottom number is. When you find the derivative of it, it'll disappear. All right. You guys at home are free to go. Have a great day. You're awesome. You've been a wonderful audience. You guys are stuck with me for 19 minutes. What do you want to do? All right. I've stopped. You can go. But then you would have missed something. Okay.